Okay, so if everyone's ready, I think we can start. It's time. Thank you. So the second talk today is the second talk of Nitin Saxena. The first one was last Friday, and today it will be about demystifying the border of depth-3 circuits. So you can start whenever.
Okay, thank you, Thomas. Can you hear me and can you see the slides?
Yes.
Yes. Yes.
Okay. So, yeah, so today I will continue with the type of study I started on Friday. Authors are the same, but these slides were used by Pranjal, created and used by Pranjal for some other talk. I'm recycling them. So thank you. Thanks to Pranjal. So demystifying the border of depth-3 algebraic circuits is the title. If you don't know what the mystery was, this also I will define at some point in the slides. You are welcome to ask questions at any point of time. Don't wait for the end. So I'll define some basic models and then I'll go to border complexity, which was not covered in the first talk, and tangentially mention geometric complexity theory. But I'm sure you have seen enough of GCT in this conference. And then I'll directly jump to our results and give some ideas how the proofs were done. Yeah, so the overall, I mean, the long-term motivation of GCT and in general, these kind of problems is P, proving that P is different from NP. And the techniques using probability and Boolean circuits have some barriers, identified barriers, which are called the Rasburov-Rudick natural proofs barrier. So people try to go up around it by using more and more algebra and geometry. So with this motivation, Mulmule and Soni proposed GCT1. So GCT1 basically builds on the Variance model of algebraic circuits. So instead of starting with Boolean circuits, you start with algebraic circuits which add and multiply polynomials. I mean, they have gates which are addition multiplication gates in the polynomial ring. So ultimately a polynomial is being computed, and then you can ask questions which are kind of simpler questions than P not equal to NP, which is now called Variance P not equal to Variance NP conjecture. And one thing, I mean, the starting point of GCT is different from simple algebra because in an attempt to use algebraic geometry, it starts using or introducing this notion of approximation of polynomials. So basically, I mean, to define a variety, it actually, instead of just looking at circuits, it looks at also the limit points of the circuits. Okay, and in defining these limit points, you basically come up with this definition of border complexity, which we will formalize. It's not very difficult to formalize actually. So we'll formalize it in one way. There are actually many ways to formalize it. So this analytic way is the basic motivation, and that comes from limit points. In this talk, we will mostly be concerned, we will define and mostly be concerned with the algebraic definition of border complexity instead of the geometric or the analytic one. So we'll not get into limits. We will just define it kind of algebraically. The advantage is that it will be a definition independent of the field. It will work for any field. Yes, and then GCT2 and GCT X's, they then study these algebraic circuits and their questions in terms of approximative size or border complexity, and then also introduce representation theory, which you have been seeing in other talks, just in the previous talks, for example. So we will not be discussing that, although our final result of this paper, of this talk, can be rephrased in purely algebraic geometric terms as well, which maybe I will mention at some point. So GCT, for example, Aronson says that this can be called the string theory of computer science. And I'm not sure whether it's a joke, but I feel that the comparison is not too bad, because just like string theory tries to unify all parts of physics, GCT is such an expressive language that almost anything in computer science, in algorithms, in lower bounds or measures, can be rephrased in the language of GCT. Okay, so it's highly expressive, which is both an advantage and could be a disadvantage, because even simple things could look very complicated in terms of GCT. Advantage could be that you may be able to invoke a generalization or a more general principle to prove lower bounds or to find algorithms. So yeah, just I guess the bottom line of this statement is that it's a very, very expressive language and uses many areas of math. Okay, so this I did last time also. You now very well know what algebraic circuits are. In the leaves, we have the variables. And in the internal gates, you have two types: addition and multiplication gates, and constants sit on the wires. So when they sit, they multiply the output. So whatever is the output here, it gets multiplied with 1/3. Okay, so this way you can, this is a complete model. You can represent any polynomial in the polynomial by a circuit. What is the size? So size is the graph size, which is number of edges plus nodes, edges plus vertices. And the size of a polynomial, or the circuit size, the circuit complexity. Right? Naturally, this will be the minimum sized circuit. So you optimize the circuit for a given polynomial f. If you don't know this term from before, then one confusing thing here is that when we talk about size of a polynomial, we generally mean a family of polynomials. Okay, so we actually never talk about a single polynomial. We always have a family in mind. And then for the family, we talk about circuit complexity, because I mean, it will not make sense to just talk about n equal to 10, for example. To see the asymptotics, you have to see n equal to 10, 11, and so on till infinity. Right? Only then can you say that, okay, this family is hard or this family is easy. Just looking at constants will not help. So this is why always size of a polynomial or circuit complexity of a polynomial always means it hides in the definition of family. It's never a single polynomial. It's actually an infinite number of polynomials. And depth of a circuit is just the number of layers. So amongst the polynomials, which ones are easy and which ones are hard, right? So this is the question that motivates us. And Variant formalized the easy ones by saying that look at the polynomials, which again, this is a polynomial family. So look at a polynomial family where the size of the circuit, optimal circuit, and the degree both are bounded by n to the c. Okay, so both are poly in the number of variables. And collection of such families is called VP. Okay, variance polynomial time. This polynomial, variance P, which is now not in terms of time, but in terms of the size and the degree. They are both upper bounded by a polynomial. C is an absolute constant, independent of n. So, I mean, examples are many. For example, you just multiply variables x1 to xn. This is very simple. This is essentially a single multiplication gate. Or look at few powers of x1 to xn. This again is just few multiplication gates, which you are adding by a single addition gate. So these are obviously low degree and simple. The circuit is quite small. And more interestingly, if you go over all the subsets, even this is simple. Although this has a lot of monomials, it has 2 raised to n monomials. But still, as a homework exercise, you can show that its circuit is simple. Okay. In fact, I show it right here. It completely factorizes. And yeah, so why is the degree upper bounded? So one example is what may happen in a circuit is you may be able to compute x to the 2 to the n, because you may just keep on multiplying things. Okay, so computation goes from bottom to top and you keep on multiplying. So after very few multiplication gates, depth n, you will be able to compute x to the 2 to the n. So which is a very high degree. Okay, so these exponential degree computations or polynomials we want to exclude for the time being, and which is why this VP has an extra restriction on the degree. I mean, these are also valid circuits, but and valid polynomials, but yeah, this we will study some other time. Okay, so VP and VNP are not interested in this family. They limit the degree to polynomial. Next is the determinant polynomial. This is a special kind of a circuit. It in fact I'm mentioning it because this will define its own model of computation. Okay, so determinant, as you know, is a sum over all the monomials with respect to permutations. Okay, so the variables are this xij, I and j going from, I mean, this is an n cross n matrix, so n square variables. And the determinant, as n varies, this is the determinant family of polynomials, the determinant polynomial family. If you don't know this, you will need to show this. It's a non-trivial thing that determinant is a universal model. Okay, any polynomial can be written as a determinant. So determinant is universal, and it can compute any polynomial. Any polynomial can be written in this way. So hence, it makes sense to define determinantal complexity of a polynomial. Okay, this is always finite. It's basically given a polynomial f, can you write f as m cross m determinant? So if you can, then the determinant complexity is defined to be less than equal to m. Okay, so it is the smallest m such that m cross m matrix computes your polynomial. That's the determinantal complexity. For example, the monomial x1 dot dot xn has determinantal complexity n, because you can just do this by a diagonal matrix. So polynomial, the model that determinant polynomial defines, this is called VBP. Okay, it stands for Variance Branching Program. It's basically, there are multiple ways to define it. There are at least 3 ways. So right now I am only using the determinant for its definition. Okay, so VBP is the set of those polynomials which have determinantal complexity polynomial in N. That's the definition. Okay, but there are also other ways to define it. Let me not go too much into that unless you have questions. And it's an open question. It's a conjecture that VBP is different from VP. Why is VBP in VP? Well, this you have to, again, I leave it as an exercise to show that determinant can be written as a small circuit of poly size. And so that will show that VBP is in VP, and it's a conjecture that VBP is strictly smaller than VP. Okay, so VP has polynomials which are which will require super poly dimension determinant. Although guessing such a candidate is not easy. So think which kind of a polynomial will have this property. So by small ABP, we will mean also small determinantal complexity. And this, of course, is very important when you are doing linear algebraic computations. You are computing volume because determinant captures volume in geometry. And also when you are counting planar matchings, for example. Yeah, so these are kind of the easy polynomials, right? Determinant is an easy polynomial. Polynomials in VP are easy, VBP are easy. So any questions till this point? Any general questions?
Yeah.
Okay. So then what are the hard polynomials, right? Let's focus on them now, although all these things will be conjectural. So a hard polynomial will be one where the circuit size of Fn will be super poly. So that is denoted by this notation, n to the little omega 1. So little omega 1 means that it is some growing function of n, like mu n. And mu n tends to infinity. Okay. So that kind of a complexity we are looking for, and then we will be convinced that Fn is a hard polynomial. So which polynomials have this feature? So in fact, you can show that random polynomials always have this feature. If you take all the monomials and give them random coefficients, in fact, you can even give them just 0, 1 coefficients. That polynomial with high probability will be very hard. Okay, not only super poly, but maybe even exponentially hard. But the challenge in algebraic complexity is to find an explicit one. Okay, so not random coefficients, but coefficients which are in some sense easy, or they should have a non-trivial algorithm to compute. I don't mean polynomial time by that, but just something which is better than the trivial time complexity or space complexity. Okay, so, and the random one is not of that type. So we want an explicit polynomial which has circuit size super poly. So one such candidate we have to mention, and that is called permanent. Okay, permanent is determinant without the sign. So this sign which used to be present here is now +1. Okay, that is the difference between determinant and permanent. And again, you are adding up all these monomials. Each monomial corresponds to a permutation of an coming from an n by n matrix. And permanent again is universal. It's a universal polynomial. Any polynomial can be written as a M cross M matrix permanent, where the entries are linear. Entries are either they are linear functions or they are even constants. And this, I feel, is not completely trivial. You have to do this as an exercise to be convinced that both determinant and permanent are universal polynomials. And now you can also define permanential complexity. So permanential complexity will be for your polynomial, what is the optimal M cross M matrix such that permanent is equal to F. So that M minimum optimal M will become permanential complexity. And yeah, so just like determinant has its own class, permanent has an even bigger class, which is called VNP. Okay, so VNP is the class of those polynomials, polynomial family again, such that the permanential complexity is poly n. Okay, so that's the class VNP. So we have VBP, VP, and VNP defined. And yeah, this VNP and permanent is connected to enumeration, for example, counting matchings in a graph. Okay, that is a question which naturally gets computed by permanent, and for similar reasons also in stochastics and in probability theory, permanent pops up. But those physical interpretations are not as powerful as that of determinant, which is why which is why we still don't have an algorithm to compute permanent. Okay, so computation of permanent is conjectured to be very, very hard. As hard as you can imagine, exponentially hard. Yeah, so this again is not completely trivial, but you can take it as an exercise that VP is also contained in VNP. Okay, so determinants are contained in circuits, small circuits, and small circuits are contained in small permanents. And Variance conjecture says that they are all different. Okay, so Variance conjecture, first of all, it says that VP is different from VNP. That's the conjecture. You can also take it as VPP different from VNP, which will be a question of separating determinant from permanent. Okay, that determinant cannot be written as, well, permanent cannot be written as a small determinant. So these are the two questions about permanent. And the third question is VBP different from VP. Okay, that's a question about determinant that, or I mean, there is a polynomial in VP which will require large determinant order. And the candidate is not very clear with what polynomial it should be. But this you can try to work out. So these three things are, actually there are only two inequalities. The third is implied. So these three classes are conjectured to be all different. Is this conjecture clear? Any questions about the classes and the comparisons? Already we have too many terms defined. So if you have questions, feel free to ask. Some here are experts and others are not. So don't feel shy. Okay. Okay, then I'll throw more definitions at you since you are so good. Yeah, so so Burgesser showed that these algebraic conjectures are somehow related to the Boolean conjectures, but not the best one. So it is not directly related to P not equal to NP. But it's related to something called P/poly and NP/poly. Okay, if you look at the non-uniform version of P not equal to NP. So this you can call the non-uniform P not equal to NP. Which will be a kind of a strengthening of P not equal to NP. No, I'm not sure whether it's just strengthening or incomparable. But anyways, this P/poly different from NP/poly will imply that these conjectures are variant, that VBP is different from VNP and VP is different from VNP over finite fields. Okay, this is a theorem over finite fields, but if you want to prove this over zero characteristic field like complex field, then for some weird reason GRH is required. Okay, so assuming generalized Riemann hypothesis, these Boolean conjectures, they imply algebraic conjectures. So what this means is that if you want to prove these natural questions in Boolean complexity, then you have to go through algebraic complexity. These algebraic complexity results will also be, their proof has to be passed through. You cannot skip them. So it makes sense to then, if you are interested in algebra, it makes sense to then study these algebraic conjectures on its own without worrying too much about the original P not equal to NP question. So that is what we do. And the state of this is not very good, but there has been a recent breakthrough where separations were shown for circuits, the circuit model assuming constant depth. Okay, so the depth of the circuit, if you restrict, so from input to output, if this is constant, let's say this depth is 100, okay, then and these models are also, by the way, pretty difficult. They are as good as the general models. There are very specific theorems that connect depth-3, for example, with depth general. And what was shown by Lemayesh, Srinivasan, Tavanas last year is that there are explicit polynomials which require super polynomial constant depth algebraic circuits. And this explicit polynomial is essentially like, it's actually a simpler form of multiplication of matrices, what is called iterated matrix multiplication.
Hi, Nitin, can I ask you a question? This is Arkadev.
Yes, sure. Yeah, Arko, hello.
Yeah, hi. So just the question was, you showed in your previous slide that lower bounds on Boolean circuits would imply lower bounds on algebraic circuits.
Yes.
So this thing, it doesn't preserve depth, is it? Like suppose, can the proof go through assuming, suppose I have lower bounds for constant depth Boolean circuits, can that be made to yield lower bounds against constant depth algebraic circuits? I'm guessing the answer is no, because otherwise the result, the breakthrough result would have been known before.
No. I think the problem is this P/poly still is a good class. It's a natural class. But I think this NP/poly is a messy class. So maybe results for those will not be easy even for constant depth, I'm guessing. Don't you think this NP/poly is a bit weird?
I see. You're saying what would be the analog of that result in the okay, I see. So that's specific. So it doesn't, for example, if I just showed a polynomial, so if I just showed that some Boolean function requires large super polynomial size circuit in the Boolean world, this may not imply anything in the algebraic world.
Yeah, unless you work with SAT.
I see.
I think you have to show that SAT doesn't have P/poly, that kind of a thing. So just working with an arbitrary polynomial of your choice, I don't think it will help.
Okay.
Yeah, I think that is the problem. By the way, these proofs are not very illuminating. So this again, I am leaving as an exercise. These two theorems are actually quite simple. You basically start with this contrapositive. Suppose that permanent has a small algebraic circuit, and then you make it Boolean and solve SAT. That's the kind of proof idea for this. So it's not a very illuminating proof. So I don't think this helps too much, except it gives a concrete connection from Boolean to algebraic. Any other questions?
Thanks.
Sure. Okay. If students have any questions, they can also ask. I'm sure some things here are new. Okay, so yeah, that's the LST 2021 result. And yeah, during these pandemic years, there have also been results about algebraic natural proofs, basically investigating these questions. Can there be, I mean, first of all, you have to define what is a natural proof in the domain of algebraic circuits, and could they exist or would they not exist for the VP-VNP question. So there are papers of that type. Right. So then, so now I'll move to the main attraction of this talk, which is some interesting border classes, and we will try to ultimately de-border them, which is we'll make them exact. Okay. So from approximative models, we will go to exact models. That will be our final goal. I don't think I have enough time. So let me move a bit faster now. So, so how do you define this complexity for approximative models, and how do you define approximations in algebra? So one nice example, or the simplest example you can think of, is Waring rank. So what is Waring rank? For a polynomial H, Waring rank is essentially given by this identity or by this representation. You write H as a sum of dth powers of linear forms, LIs, and this, so H also you can assume is a D form. So write a D form H as sum of D powers, and what is the minimum number of powers needed? That's R, right? So R is called Waring rank of H. And yeah, so here R is called the Waring rank of the polynomial. And yeah, so if you study this, it's not, again, it is not trivial, but it needs some exercise to show that Waring rank is always finite. Okay, any polynomial can be written as a sum of D powers. Any D form can be written as a sum of D powers. Finitely many D powers. So this will always be a finite quantity. And you can guess usually what this R will be. Okay, usually this R will be an exponential quantity. And the corresponding computational model is called sigma wedge sigma model. Okay, sigma wedge sigma is sum of powers of linear polynomials. And in the top fan in here is R. This is the Waring rank when you are computing H. This is also called depth-3 diagonal circuits. So that's the model. Basically, the top fan-in is what gives you Waring rank. So why did I take Waring rank as an example of approximation? Because this currently is an exact model, what I defined. So if you look at Waring rank of x square y, it will come out to be 3 or less. Because for 3, you have this example. You have this representation of x square y, which is basically sum of 3 powers, x plus y cube, x minus y cube, and y cube. As an exercise, you can show that it's exactly 3. It's not a difficult exercise. If you write x square y as a sum of 2 cubes, you can factorize and you can give an elementary argument that that is impossible. So this essentially is the best representation for x square y. But if you start thinking in terms of limits, okay, you introduce an epsilon and look at this expression, x plus epsilon y cube minus x cube. So this will expand as follows. And if you set epsilon to 0, you magically get x square y. Okay, so this we can call, in an inspiring way, we can call it h sub epsilon. And so this you can think of as an infinite family of polynomials, which in the limit become x square y. Okay, and each of these infinite polynomials, they have Waring rank only 2. Okay, so we have been able to construct an infinite family of Waring rank 2 polynomials, which in the limit become h, but that h doesn't have Waring rank 2. Right, so this is the interesting phenomena which this type of approximation throws up. And we will be interested in this. Okay, we will be interested in getting to our favorite polynomial h in the limit. Okay, and so note that this h epsilon is not defined for epsilon equal to 0. This is undefined for epsilon equal to 0. Yeah, what do I mean by that? So, well, if you calculate everything out, then you can set epsilon to 0. But in the intermediate computation, since 1 over epsilon is sitting, that doesn't make any sense, right? Because 1 over 0 is infinity. So we are essentially in this representation multiplying by infinity. So how can we multiply by infinity? So, I mean, intuitively, what is happening is that inside you have this x cube minus x cube, so that is 0. So this is kind of infinity multiplied by 0. But obviously, we cannot formalize this. So what we say is that we will never set epsilon to 0. But if epsilon is thought as a real number, then we will take it infinitesimally small. Or in other words, we will take this infinite family of approximations. And this ultimately is the representation of h. Okay, so so this is the spirit of border or limit point. That in exact computation, the measure may be large, which is Waring rank. But if you start approximating, then the measure becomes smaller, which is in this case 2. So this is a good example. Waring rank is a good example of a measure which you can approximate and see how it can help. Okay, so this picture shows the transition, the limit point. So Waring rank 2 is a smaller bubble, and Waring rank 3 is obviously a bigger bubble. And this x square y is sitting in the middle. Okay, so when you start taking approximations and limit points, then it will come at the boundary of Waring rank 2 and won't reach Waring rank 3. Okay, so yeah, any questions about this illustrative example? I have still not defined approximation, but you sort of get what we want to say, right? Okay. So let us now formalize this. So we can call border version of Waring rank. So border is because that example sits at the border. So border of a measure, in this case, Waring rank, is defined as the smallest n such that each your polynomial each can be approximated arbitrarily closely by polynomials of Waring rank n or less. Okay, so if you can write each as each epsilon tending to 0. Okay. Yeah, and in terms of the Zariski topology, what this set is, the set of each with border Waring rank n or less, this now becomes a closed set. Okay. And think of each as actually the coefficients defining a point in the space. So think of each as just a point. Okay, so these points and this set of points xn is now a closed set. So it's geometrically very nice. This was not the case if you looked at the set of each with Waring rank, exact Waring rank less than equal to n. Okay, so this set is a subset actually of xn, and as we saw, it's a proper subset. Okay, so that subset we have now made it closed, Zariski closed. That is what happens geometrically, and this is what we do with any measure. Okay, in particular with size, we'll do that. Yeah, before I move to size, so if you suppose you want to show that a border Waring rank of P is greater than n, right? So you want to it suffices to show that P is not in Xn. So for that, you may try to find a continuous function f that vanishes on Xn but not on P. Okay, so this kind of gives you an abstract tool to prove lower bounds via continuous functions. Okay, that's the nice thing about closed sets. So yeah, with this toy example, now you can take any measure gamma, for example, circuit size or determinantal complexity or permanent complexity, etc. And we will specially like size. So you can take any measure and define its bar, the border version, right? So gamma bar H is what you can now define. This will be the smallest n, such that H can be approximated arbitrarily closely. And this arbitrarily is actually, yeah, I mean, you have to have this kind of infinite family, right? This H epsilon is an infinite family. So if you can calculate H, you can approximate it this well, then where gamma of H epsilon is less than equal to n. Okay, so the classical complexity of H epsilon is at most n, and that gives you the approximative complexity of H itself. Is this definition clear? So this we can do with any gamma now. And that's the condition that has to be met. So we use gamma on the left-hand side and we define gamma bar on the right-hand side. Okay, you look at gamma of H epsilon and that gives the definition of gamma bar of H. So for example, tensor rank, you can define corresponding to a border tensor rank, and so on. And this is actually related to matrix multiplication exponent. Okay, border tensor rank is something that is used there. Okay, so yeah, now let us talk about approximative circuits, which is our, finally, that is our object of interest. So these approximative circuits we will formalize by using the same epsilon, and now working over the function field. Okay, so f epsilon is the function field. So you are allowed to use functions like these, and these will be treated as constants in the circuit. Okay, so 1 by epsilon cube or epsilon by epsilon cube plus 1, these are the constants in your base field. So we have expanded our base field. Instead of f, we have f epsilon. And using these constants, now you can draw your circuit, and you can, it will calculate G. Okay. Size is just number of vertices and edges. And right, so D now can be written as, in case it's a polynomial. Okay, it may not have been a polynomial, but we will always be interested in only the case where G is a polynomial. So in the case where, so remember, I mean, this may be a bit confusing, that inside the circuit we are using fractions like 1 by epsilon, but still they may cancel out, and in the end we may end up with a polynomial in epsilon. Okay, that's the case we are interested in. So when that happens, we can write G as a polynomial in epsilon power in epsilon. So basically, the coefficient of epsilon to the I is Gi, which is itself a polynomial in variables x1 to xn. And we can now look at epsilon equal to 0, and that gives us G0. Right, so we can kind of do this illegal operation, epsilon equal to 0, which makes the circuit constants illegal, but the final output still makes sense because it is G0. And we can say that G0 is the polynomial which is being computed in an approximate way. So yeah, let me come directly to the definition. So this motivates the definition of algebraic approximation via circuits, or computing a polynomial H by an approximative circuit. So the approximative circuit will be G of x epsilon. It will be, ultimately it will be, I mean, inside the circuit you may divide by epsilon, but ultimately it will turn out to be a polynomial in epsilon, such that when you set epsilon to 0, you get H. Okay, so H is being approximated by these G epsilon. So alternatively, you can think of this. Okay, H actually has this infinite family where epsilon is taking smaller and smaller values. If you want to think in terms of real analysis, then epsilon is a sequence of real numbers which is tending to 0. So you get this sequence of G epsilons which ultimately become H, and at all points of time, G epsilon has small size, which is size S. And that is called the approximative size of H. Okay, so we will denote it by size bar. This is the approximative circuit complexity of the polynomial H. And this naturally, it is trivially smaller than size of H. It is at most size of H. Is the definition clear? Okay. So this definition doesn't tell you anything about how large the degree of epsilon could be. So using kind of this Bezout theorems bounding the degree of a variety, it can be shown that you will never need degree of epsilon to be more than exponential. Okay, just degree 2 raised to s or 2 raised to s square suffices. So you can assume that epsilon is has degree exponential in s, and that is what is being done inside G. But this is not very helpful computationally because it is kind of introducing exponential precision in your circuit. It's and then you cannot really make it exact, right? If you try to make it exact, then your circuit will blow up exponentially. So that is why this this is not yet completely understood. How far is size bar from size? Okay, so trivially what we get is that trivially we get this comparison, that size bar is at most size and size is at most exponential in size bar. Okay, so there is an exponential gap in our understanding. And I don't know of any good convincing candidate age where this is really exponential. But a priori, it could well happen. I mean, for example, if you saw in Waring rank, that Waring rank actually fell when we used a border of Waring rank. So in the case of circuit also, hypothetically or potentially, it may happen that the approximative circuit size falls by a lot when we use approximations.
Sorry, Nitin, one more question.
Yes.
About Waring rank, what do we know? How far apart can these two things be? The approximate Waring rank, if I may say so, and the Waring rank?
Yeah, I know it's a good question. I think it's an open question.
Even that is an open question. Okay.
Yeah. I think it's an open question. So Pranjal has some intermediate results, but this is largely open, right, Pranjal?
Yes. Actually, it is conjectured that they are polynomially related, border Waring rank and Waring rank. But I think, at least formally, I think even just border Waring rank 4 or something is known, and I have some results which essentially shows that for constant border Waring rank, you can show that Waring rank is polynomial or something like that. But yeah.
Because
so you have a gap of like, I mean, so did you mean that there is a polynomial with constant approximate?
Yeah, so I could show that I think if you have border Waring rank, let's say k, then Waring rank will be something like d to the 2k or something like that. So which is bad because, yeah, something like that.
I see.
Yeah. So I just want to point out that in Waring rank definition, this sigma li to the d, you never need to go beyond, let's say, n plus d choose d. So the space, that linear space that you are looking at, is only exponential. So everything is below that, but we don't have a good comparison between border Waring rank and Waring rank. So in the worst case, it could be exponential. In the best case, it could be polynomial, and we don't know which is which. Yeah, so Ram Prasad says that x to the dy, if you look at that instead of x square y, then the gap will be d versus 2. So it will already be a non-constant reduction. Yeah, so as I said, we don't have a very convincing argument that you get exponential advantage by approximation. But I mean, from the definition, everything is possible. I mean, maybe there are examples where approximation gives you exponential advantage, but we don't know of such examples. Even
and you're saying that's open, and you're saying that's open even for a computation model like Waring rank.
Yes. Yeah. So Pascal is asking a question. Is it clear that we can restrict to approximations by rational functions in epsilon? Yeah, so this is actually, I think, a result from the 1980s in algebraic geometry, that we can restrict to just f epsilon. I don't think this is a trivial thing, but it follows from certain results in algebra or algebraic geometry.
But could it change the complexity of the resulting circuit if you allow say approximations by algebraic curves? You might think that you could have maybe a faster approximation than with rational functions. I'm not sure that makes sense, but
yeah, I'm not sure. So I mean, you can use other functions in epsilon, but they can all be reduced to this epsilon to the 2 to the s square expressions inside f epsilon. I mean, they basically look at Laurent series, and in the Laurent series, it is shown that both the negative and the positive exponents can be bounded.
okay.
By Bezout degree bound.
Also, I think ultimately epsilon in this algebraic circuit is essentially, I mean, just a constant, right? So if you try to use something else, so eventually, it's like a constant. So
yes. So actually, so the short answer to Pascal's question is that you can allow any function in epsilon. The border size will not change.
Okay.
Yeah, border size actually remains the same. All those definitions are equivalent, essentially. That can be shown. But more interesting thing is, from border size to size, what is that gap? And that we really don't have good examples. We don't know what kind of a jump it is. So we conjecture that, well, it's always possible to go from approximative to exact in a polynomial blow up. That is our meta conjecture. And this is what we exhibit in depth-3 bounded top Fannin circuit. So this is the term we invent. We call it debordering. Okay, so debordering is just a manifestation of our meta conjecture that all approximative circuits can be converted into exact circuits with a polynomial blow-up. So given a nice class C can be deborder C bar. That is, find another nice class, exact class D, such that D contains C bar. Okay, this is what we want to do. So we conjecture that this can always be done. So obviously, big ticket results will do this for VBP, VP, diagonal circuits, VNP, and so on. We don't have any of these big ticket results. So we will just give you small ticket results, which is, let me directly come to, I think my time is already up. Let me at least show you depth-3 and skip all this. So what is border depth-3? So depth-3 circuits is this notation, sigma pi sigma. Top Fannin is K and the product Fannin or degree is D. So the size is bounded by K and D. N is the number of variables. So in a way, this bottom sigma has Fannin N. So you see all the parameters K, D, N. And so you are basically computing this sum of product of linear polynomials. And so we will, in this talk, we will take K to be constant. And you can ask the question whether for K constant, this model is a universal model. Okay, can, for example, sigma 10 pi sigma, can it represent any polynomial? And the answer for that is no. Okay, it can be shown that it's just impossible to represent some polynomials as sigma 10 pi sigma. So this is not a universal model. But what about the border of this? Okay, if you take the border of sigma pi sigma, sigma 10 pi sigma, then it becomes universal. That is an amazing result. So this is a result by Mrinal Kumar that already sigma 2 pi sigma border is universal. If you are willing to pay exponential degree on the pi fanning. Okay, so then you can represent any polynomial p can be written as sigma 2 pi sigma bar. So this is already a big difference between the classical sigma 2 pi sigma and the border version of it. So in a way, if you start approximating sigma 2 pi sigma, then all the polynomials are covered. Without approximation, very few are covered. Is this statement clear? It may come as a surprise if you haven't seen this before. How is the approximation helping? So that is a neat result, which, and in fact, we have included in this slide. But since we don't have time, I will skip this. You can read the slides later. And the purpose of this talk ultimately was to show that. So this theorem 1 is our main result, that sigma 2 pi sigma bar is complete, but it is also not very hard. Okay, we actually show that anything that sigma 2 pi sigma bar computes can also be computed by VBP. That is, determinant complexity is small. Okay, so this on the left hand side you have approximation, on the right hand side it's an exact model. So we have debordered. In the spirit of our meta conjecture, we have been able to deborder these approximative depth 3, assuming that the top fanning is constant. Okay, this is not we are not saying anything about sigma pi sigma bar. That will again be a big ticket model. If we can deborder it, it will be very interesting. But assuming the top fanning to be constant, we are able to achieve that. Okay, so for arbitrary constant k. Any questions? So that's our main result. And I think I should conclude now because.
So one question.
Yes.
Yeah. So here you're saying that this D is polynomial in N. So in the sense of universality that you mentioned in the previous slide,
Yes.
that will not hold here.
No. So see, here you have to, you will be given a sigma 2 pi sigma bar circuit, right? So we will talk.
A family of circuits. Yeah.
Yeah,
okay.
yeah. So we have to talk in terms of what is given to us. So whatever is the size, in terms of that size, there is a small ABP.
Mm-hmm.
And when we talk about completeness, then we don't restrict anything. Then we only have to show finiteness.
Right.
Yeah. So I understand your question, but here, I mean, completeness is about finiteness, and here we are interested in upper bounds. That
yeah, no. So what I really meant was that the class which you have debordered is not still expressive enough.
no, but with respect to what parameter? See, that is the question.
So n, if I take n to be the number of variables and little d to be the degree, I want to express any homogeneous such polynomial, maybe using bordering. Then I can do that, but I may require large intermediate polynomials. So,
Correct.
and I can approximate. And
Yes.
now I want to answer the same question. Can I not approximate? But then that would be answering a much more, a much bigger question, I guess, because you're asking whether every such polynomial is.
Yeah. So the question you are asking is the third question, which is the lower bound question.
Right.
Yeah. So the first question was completeness question. Second, which we are showing, I mean, the first was shown by Mrinal. Then second we are showing is about upper bound, and the third question that you are asking is about lower bound. And believe it or not, that also we will prove. So we also will prove that if you want to write even basic polynomials as sigma 2 pi d sigma bar, then d has to be exponential. Yeah, so we also have lower bound results, but yeah, that is an upcoming result which Pranjal will present this week.
So when D, but the top fan-in would still, you would restrict that in that lower bound result, the top fan-in would still be restricted to 2, is it?
No, to k, constant k.
Okay, so for any constant, so you're saying that there is a polynomial P, which is in this sigma 2 pi d sigma bar, but for any constant k, it is not in sigma k pi d sigma unless d is exponential.
Yes, yeah, a very explicit polynomial. In fact, I will present the result in the conclusion. A very explicit polynomial, yeah, which if you try to write as sigma k pi sigma bar, then you will need exponential size.
Okay.
Yes. Yes, but before that, I mean, this upper bound is also important because this is telling you that when the degree is polynomial in, I mean, it's a parameter in the input, then these approximative polynomials can already be computed by an exact algebraic branching program. So this is the debordering result. I was interested to give you the proof sketch, but now you have to read it on your own. Let me skip it. Yeah, so this basically this is the DD. In fact, here we call it the DDIL technique, which we devise. So we basically start with let's say fan-in 2, right? So T1 plus T2. We start with this equation, and we divide by T2, and then we differentiate by a variable, and we essentially reduce, I mean, in a way, we reduce T1 plus T2 to T1. Okay, that's the reduction. We reduce the fan-in from 2 to 1. And in general, we reduce the fan-in from K to 1. This is what we want to do. And when we do this, we will lose a lot of information. But we will show that still somehow we will be able to go back. So from here, we will still be able to go back from where we started. Okay, so we will actually be able to rewrite F as an ABP. That is what this technique does. But I cannot give the details of this. So that was theorem 1, and we have we can also do identity testing for the same model. Yeah, so the identity testing theorem is, let me just state it. Yeah, so theorem 2 is this. So basically this for sigma k pi sigma bar, there is no non-trivial hitting set or black box PIT known, because actually it wasn't even known how difficult these polynomials are. It was possible that this model was computing very difficult polynomials, and then of course we cannot easily get hitting sets for very difficult polynomials. So our method is actually strong enough that it shows that these polynomials are not difficult, first of all, which is their ABP. Actually, for ABP, we don't have currently PIT algorithms, but by using the proof details, we are able to get a hitting set as well, because these are very specialized ABP. So for those special ABP, we are able to get a quasi-polynomial time PIT. Okay, so this was also an open question. Nothing non-trivial was known before this. Any question? Right, so then I will conclude. Sorry for the delay. Yeah, so this is the last slide. So, so we have shown that anything this model computes can be computed by a VBP, and we get a quasi-polynomial time hitting set. And the third question, which was whether this model is different from VBP. These lower bound questions separating these two complexity classes. For this, we have this upcoming result, which Pranjal will present this week, where we give a very refined separation between sigma k plus 1 bar and sigma k bar. Okay, so we show, and this is an exponential separation. So we show that the simple polynomials are there in k plus 1 top fan-in border, depth 3, which if you try to write, if you try to reduce the top fan-in from k plus 1 to k, then you will require exponential size. So this is a exponential top fan-in hierarchy theorem. So thank you.
Nitin, I have one question. So in your thing, the way the approximate circuits was defined, you needed G0. But what if you had, say, epsilon raised to minus 10 something plus epsilon raised to minus 9 and all the way?
Yeah, we have those. Yeah.
You are looking at epsilon raised to minus 10 coefficient. And that is the
you can also multiply, no? So let's say you can
but
just
then you'll increase this thing, no?
Just plus 1 or something like that, because epsilon is constant, so it's just one age or something like that, just plus 1 or something. I mean, when you are talking about general algebraic
you need to multiply it in the end, no? That's what.
Yeah, just no, in the maybe
top,
no? Okay, I mean,
you can't multiply it before you unfold it, no?
No, I'm saying that over the edges, like let's say the top gate is plus, right? And then there are edges coming out. So and the top, all the edges you can just put, let's say, epsilon to the 10. Putting epsilon to the 10 means you are just multiplying everything by epsilon to the 10, right? Okay. So that just shifts, no? Because just writing, because whatever below you just adding. So now you are just you just put epsilon to the 10 in the edges. Yeah. That just
right. So I guess the thing you have to remember is that you may do 1 by epsilon to the 10 inside the circuit. You can do these things, but ultimately what you output, this has to be the target polynomial f plus
epsilon
an ideal in epsilon.
Correct.
Yeah, this has to be an ideal in epsilon. So this is f epsilon x bar. So this you cannot have 1 by epsilon, because if you had that, then epsilon equal to 0 will not have any meaning. So ultimately you want to make sense of this in terms of setting epsilon equal to 0. So the final result should be well defined at epsilon equal to 0, which means algebraically you are looking at the ideal generated by epsilon. But inside the circuit, you can divide by epsilon to the 100 and so on. So all that is allowed. Yes. So it is a very basic question whether all this helps. Does it help to compress the circuit complexity? So that is so our conjecture is that it doesn't help. And that we are showing in this very humble circuit model.